Welcome to this video on Module 4, Internal Energy, Enthalpy and Specific Heats in the Thermodynamics class of Spring 2020. We have seen the idea of internal energy before, which I have referred to as many times. Internal energy is the sum of kinetic energies associated with molecular motion, or in other words, the motion of individual molecules, which can be translational motion, rotation, vibration of molecules. We have also seen that internal energy is proportional to temperature. That is, U is proportional to T. We know that internal energy is a state variable. Energy is a state variable, meaning if you have a process, let's say pressure, specific volume, go from state 1 to state 2, the change in internal energy U is simply the internal energy at state 2 minus the internal energy at state 1. Doesn't depend on the path to go from 1 to 2. That's what makes it a state variable and not a path variable. So we want to know how to calculate the change in internal energy for a process. Most often, for any process 1 to 2, it is easier to measure temperature changes. So you can measure T1 and T2, and that will give you delta T, which is T2 minus T1. So we want to connect delta U and delta T. Most often in thermodynamics, we are interested in delta U, and we are interested in the change in internal energy and not in U1 or U2 separately. So let's think of a thought experiment where we have a liquid that is in a sealed container, and we have a wheel that will churn the liquid, and that wheel is connected to a weight. So when the weight drops by a certain height, the work is done on the liquid, which is inside a sealed container, sealed container. So you can exactly estimate what is the change in height. So the change in height can be measured. It's easy to measure. Can be measured, and we can put a thermocouple in here. That will give us the temperature change directly. So where are we? For the liquid, we will assume that the container is well insulated so that there is no heat transfer to or from the liquid. No heat transfer to or from the liquid. So Q is 0. The work done is mg delta H by dropping the weight. Okay, so we have heat change being 0, work done is mg delta H, point being it can be calculated or it's known. Okay, so if we apply the first law of thermodynamics to this liquid system, what do we have? Q minus W equals delta U, or 0 minus mg delta H equals delta U. Okay, now what you should take away from this equation is that delta U can be estimated in this experiment. Delta U known. Okay, so delta U can be calculated. We also have a thermocouple that is measuring the change in temperature. Delta T. So let's take this quantity delta U, the change in internal energy divided by the change in temperature. What is this quantity? This is the change in internal energy. Change in internal energy per unit change in temperature. Okay, so this, remember this quantity delta U divided by delta T. This quantity is called the specific heat. The specific heat is simply defined as the change in internal energy per change in temperature. Okay, and since this experiment was done at constant volume conditions, that is, the container was sealed, the liquid had no space to expand or contract, was done at constant volume, the change in internal energy divided by the change in temperature is called as the specific heat at constant volume. CV, the subscript V, denotes at constant volume. At constant volume. Okay. Now, if we do a little bit of calculus and formalize this relationship, Cv is defined as the limit in which, for an incremental change in temperature, the change in internal energy to the change in temperature becomes a derivative. So this is the formal definition of Cv. It's the rate of change of internal energy with respect to temperature measured at constant volume. Usually Cv is known, or by known I mean measured, for substances of interest, and tabulated. Cv usually is a function of temperature. Why is it function of a temperature? Because if you think of substances, like for example a substance like helium, it is a monoatomic gas. If you take nitrogen, it's a diatomic gas that can both translate, can rotate, and it can vibrate at some conditions as well. Whereas helium can only translate. It doesn't have the other 2 degrees of freedom that you associate with nitrogen. If you think of a more complex molecule like carbon dioxide, it is carbon flanked by oxygen on both sides. It can do all three degrees of freedom. So what does that imply? Because the work done may be absorbed by different motions or modes of the molecule. By that I mean it could be absorbed in making the molecules moving faster, that is translation, or rotate faster, which is rotation, or vibrate more vigorously, which is vibration. The specific heat is also a function of temperature. So it's important that you keep in mind that Cv depends on T. We'll see what exactly is the functional dependence in a short while. Okay, Cv depends on T. So if Cv of T is known or tabulated, one may compute internal energy changes as simply delta U equals T1 to T2 Cv of T dt. It's the integral of Cv as a function of temperature between the temperature of the system at two different state points, so T1 to T2. Okay, the internal energy change is of course U2 minus U1. Okay, so make a note of this formula to be used in estimating delta U calculations. So this is an important formula. Okay, now you might do a problem in intensive variable, which is delta U equals Cv dt integrated from T1 to T2, where delta U itself has units of joule per kilogram, T has units of course of Kelvin. That makes the units of Cv as joule per kg per Kelvin. Okay, you could do the same problem, or you could do a problem in terms of the extensive variable for internal energy. Extensive variable for internal energy, which is delta uppercase U, is T1 to T2 Cv as a function of dt, as a function of temperature dt. If delta U has units of joule, Cv would have units of joule per Kelvin. It really depends on what is your problem at hand. Usually we prefer intensive variables because it's easy to go back and forth. You can write the intensive version is the extensive version divided by the mass of the system. Okay, so that wraps up our discussion about internal energy, which is delta U equals T1 to T2 Cv of T dt. Okay, Cv of T is usually tabulated from measurements. Okay, so I'm going to continue next on to enthalpy. Moving on to enthalpy, very often engineering processes are designed to take place at constant pressure. To develop a natural or intuitive state variable for such constant pressure processes, enthalpy was defined. Now, how was it defined? Enthalpy is defined as U, the internal energy, plus pressure times specific volume. It's the definition of enthalpy. It's the definition of enthalpy. And if you think of it, think of a situation in which the pressure is constant. Pressure pressure is constant. So if you have a system that goes from state 1 to state 2, okay, let's say this is the PV diagram. Oh, sorry, this is the not the pressure, the temperature volume diagram. Okay, in both cases P1 equals P2 equals, let's say, P0. Okay, and we have the enthalpy change, which is delta H or H2 minus H1 being delta U plus change in the PV product. Don't think of what is PV. Let's just think of what is the change in the product P times specific volume. So I have delta H equals the internal energy change, which we just now saw how to calculate. I'll just write it as delta U plus P2 V2 minus P1 V1. I'll write this as delta U plus P0 times V2 minus V1, and this is delta U plus, what is P0 times nu2 minus nu1, or P0 times the change in volume? That would be the work done. Okay, so delta H is delta U plus W. Okay, let's draw a circle around this. From also the energy balance or the first law of thermodynamics, we do know that Q minus W equals delta U, or Q equals delta U plus W. Okay, so let's combine these two relations. Which means delta H is really Q when pressure is held constant. Q is a easily, or I should say relatively easily measurable quantity, measurable quantity. For example, you could use a heat flux sensor. A heat flux sensor can record the total, the total heat transferred in or out. Okay, so what do we have? At constant pressure, you have enthalpy change is simply the heat change. At constant volume, we just saw before that the internal energy change equals the heat change. In both cases, we use the heat change as the metric because it's easy to measure. Okay, so you can think of doing an experiment, like for example, let's say we have a gas and we have a piston that is free to move without resistance. By that I mean the pressure can be maintained constant, allowing the gas to expand or contract as necessary. Okay, and in here I have a gas. Okay, and I can heat the gas by supplying heat. I can supply heat, and I can measure. I can using the heat, I can calculate delta H. Okay, I can calculate also by measuring delta T, like we did before, using a thermocouple or a thermistor or some type of temperature measurement. Okay, we can calculate what is delta H divided by delta T. That is the change in enthalpy per unit change in temperature. And this experiment, remember, is being carried out at a constant pressure. Okay, so we are calculating delta H divided by delta T at constant pressure. We define this quantity as the specific heat measured at constant pressure. This is the specific heat. This is the specific heat at constant pressure. Okay, formally it is defined as, for an incremental change in temperature, it is the change in internal energy, it's the change in enthalpy measured at constant pressure, and we write this dH by dt at constant pressure. Okay, so Cp, like its counterpart Cv, is also dependent on temperature and is tabulated for many materials. Okay, so we have on one side, I'm going to draw internal energy. I'm going to write on the other side enthalpy. So you have U and you have H. H is equal to U plus PV. Cv is du over dt at constant volume. Cp is dH over dt at constant pressure. You calculate internal energy change by integrating over the specific heat that depends on temperature between T1 to T2. Likewise, you calculate the enthalpy change by integrating over the specific heat at constant pressure between T1 to T2. Okay, Cv is a function of temperature. Cp is also a function of temperature. And we continue this differentiation by saying internal energy is representative of all kinetic energies of molecular motion. Enthalpy is a made-up quantity for use in constant pressure processes. It's, by that I mean, it's most convenient there. It's most convenient to use enthalpy in P equals constant because delta H is simply equal to the heat change. Okay. For internal energy, it's most useful in constant volume processes. There, their internal energy change is simply equal to the heat change. Okay. So to summarize, I have delta U equals T1 to T2 CV as a function of temperature dt, and I have delta H equals T1 to T2 Cp as a function of temperature dt. Okay. All right. The textbook Sengel and Bowles talks about these concepts in section 4-3 and 4-4. I particularly ask you to refer to figure 4-24 that shows the specific heat at constant pressure as a function of temperature for different gases. Okay, I ask you to look at that figure, and what that figure shows is really like saying temperature and specific heat. So here are a bunch of gases, like there is a set of gases which include argon, helium, krypton, xenon, and radon. What are these gases? These are all monoatomic gases that look like just a helium, which is just one atom, and they just undergo only translation only. So their translation doesn't get any different at higher temperatures, or in other words, all the energy you supply goes into only exciting the translational motion of these molecules and is not going into other modes. So their specific heat is independent. I'm going to write this in a different place. The specific heat is independent of temperature for these noble gases. Okay, so Cp is a constant for these noble gases. If you look at another class of molecules, like for example hydrogen, air, nitrogen, and oxygen, you could see that their trend looks something like this. Here is temperature, here is Cp, and if you look at their trend, initially it moves like this, and then there is a steep increase at higher temperatures. So initially at lower temperatures, like this temperature is somewhat lesser than 1000, it's maybe 700 degrees Celsius or lesser, and this is at higher temperatures, 700 Kelvin or lesser. What happens here is at these temperatures, the translational, all the heat that is supplied to these molecules undergoes or is taken up by the translational motion, and at higher temperatures the energy provided goes into not only translation but also rotation and vibration. So the additional degrees of freedom take up the energy that is provided, or in other words, in order to increase their temperature at, let's say, between like saying a delta T, in which you go from 650 to 700 Kelvin, will incur you less energy, than a temperature rise from 2000 to 2050 Kelvin. Even though the delta T is the same in both cases, it will have different values of delta H because the Cp value is different. Cp is a strong function of temperature. Okay, that is, if you want to calculate delta H, you need to integrate T1 to T2 Cp of T dt. If Cp is of T is simply a constant, then that would mean delta H is Cp naught times T2 minus T1, or this is Cp naught times delta T. If Cp is a function of temperature and it is not simply a constant, then you have to imply that delta H from, let's say, 650 to 700 Kelvin is not equal to delta H from 2000 to 2050 Kelvin. So what I request you to do is look at figure 4-24 and understand that Cp depends on temperature. Likewise, Cv also depends on temperature. This is true generally for gases, and we deal mostly with ideal gases. Okay. It is also somewhat true for liquids, somewhat true for liquids and solids too. Okay. So thing to remember is that whenever you try to calculate delta H or delta U, you need to make sure that you are using the correct function for Cp or Cv, and we'll do examples that illustrate this formula. Okay. Now what about water, or what about liquids and solids? Liquids and solids, Cp, so if you take a solid, okay, if you take a solid or if you take a liquid, if you take a solid or a liquid, what you have is there is very little volume change when pressure changes. That is, these are usually incompressible. It's very hard to compress a liquid or a solid, so that the change in volume is almost zero when the pressure changes. Or in other words, if you have constant pressure, it also sometimes implies constant volume, which means Cp and Cv are approximately equal, and we just call it the specific heat. So I'm going to write this again the next page. Cp and Cv are approximately constant. We call it just the specific heat of such and such substance. So you can think of solids like iron or liquid like water. They do have a temperature difference or temperature dependence. C does depend on specific heat. There is a temperature dependence to specific heat. Okay, there is a temperature dependence, and C of T is also tabulated for many materials. And to calculate delta U, we just integrate T1 to T2 C of t dt. Okay. Now you may remember that, you may recall that while using property tables for water, we saw that there was temperature, the saturation pressure, nu F, nu G. We also saw UF, UFG, UG, and we also saw HF, HFG, and HG. Similar to specific volume and internal energy, H for a saturated liquid vapor mixture can be calculated as X times Hg plus 1 minus X times Hf. Okay, you can use similar equations that you used for specific volume and internal energy. Now, if you think of a pot of water, let's say you have some water, you supply heat, and you keep, if you think of your temperature specific volume diagram, you start out, if you are at constant pressure, you start out as a compressed liquid, you reach the point of saturated liquid, you reach the point of saturated vapor by going through intermediate states, which are saturated liquid vapor mixtures, and then you finally keep continuing heating, you will reach the state of superheated vapor. Now focus specifically on this phase change process. Okay, this is the process in which the substance goes from liquid to vapor. So usually this happens at constant pressure. Phase change happens at constant pressure, and until the phase change is constant, the temperature is also a constant. Until the phase change is complete, the temperature is also constant, and you know that it is equal to the saturation temperature, Tsat. Okay, so if you think of what is the internal energy change for a phase change process. If you go by your logic of saying delta U is proportional to delta T, then you would predict 0 because delta T is 0. You shouldn't go by that, not correct. You should go by the internal energy change being the energy of the saturated vapor minus the energy of the saturated liquid, which is UFG. Okay, which is given in the tables. UFG is simply UG minus UF. Okay, similarly you can calculate what is the enthalpy change, which is Hg minus Hf, which is given as HFG, and this HFG is exactly equal to the amount of heat supplied. This, you may recognize, is the heat required to change phase. That is, you have a bunch of liquid molecules. For them to become vapor, So to go from liquid to vapor, you have to provide the excess kinetic energy. Excess kinetic energy of molecules needs to be provided, and this is what we call latent heat of vaporization, or in general latent heat of phase change. This would be exactly equal to HFG, which is Hg minus Hf, or the enthalpy of the saturated vapor minus the enthalpy of the saturated liquid, both of which can be looked up from the tables. Okay. So we just saw how to use property tables for water, or in general any substance, to get delta U, delta H. You already know how to use it to get delta nu, to use pressure and temperature. Okay. For if you are dealing with water, you use the property tables, which is A3 to A6. Okay. If you are dealing with air or an ideal gas, you can simply calculate delta U or delta H by using the integral formulas, and the correct expression for CV and Cp. Okay. These relations are true for any substance. That is, we can start with air or an ideal gas or water. This is the definition of delta U and delta H. It's true for any substance if you know what is Cp and Cv for that particular substance. Now we have been dealing with the ideal gas as a model, because the ideal gas can be used to describe air or nitrogen at a variety of conditions. And what is the ideal gas equation? The ideal gas equation of state is PV equals RT. That is the ideal gas equation. Now what is the definition of enthalpy? It is U plus PV. That is the definition. It's true for any substance, not just for the ideal gas. Suppose we insert the value for PV into this definition. You can write this as H equals U plus RT. This is true for only an ideal gas here on. It's not true for any substance anymore. So suppose, let's say we take the derivative we take the difference or the differential of this equation. That would be dH equals du plus R dt. Okay. So what do we have here? So I can write this as dH is the partial of H with respect to temperature at constant pressure multiplied by dt. Du is the partial of the internal energy with respect to temperature at constant volume times dt plus R dt. Okay. So that is, I have a relation between dH over dt, du over dt, and R dt. So if I do that, what is dH over dt at constant pressure? We recognize that as the specific heat at constant pressure. That of course depends on temperature, and du over dt at constant volume is Cv as a function of temperature. Now remember, I use the subscript V, and usually for specific volume we use nu. Okay, this is V, the English alphabet. This is nu, the Greek alphabet. Okay. So I have, what do I have? From the previous page, I have dH over dt at constant pressure equals du over dt at constant volume plus R. Or I have Cp equals Cv plus R, or Cp minus Cv equals R, which is true only for an ideal gas. Cp minus Cv equals R for an ideal gas. Cp minus Cv equals R, a constant which is equal to the universal constant divided by the molecular weight. This is true for any ideal gas. For any ideal gas, it could be helium, any ideal gas. It could be helium, it could be nitrogen, it could be carbon dioxide, it could be sulfur hexafluoride, anything. As long as it's an ideal gas, this relation is true. Okay? So once we have this, it gives us some conveniences experimentally. One could measure only Cv or Cp and get the other. That saves a lot of time, okay? And get the other using Cp minus Cv equals R, okay? So you have this, and in general, for many substances, for many gases, in general, for many ideal gases, you can write Cp as a function of temperature as a polynomial that looks like A plus Bt plus Ct squared plus dt cubed. A, B, C, D are fit constants, and they of course vary for different materials or different gases. Okay? If this function is known, what else can you do with it? It means you can also get Cv. Cv can be calculated. Okay, number one. If you know Cp and Cv, you can get delta H, you can get delta U. That is, to summarize, if you have temperature at two different states, using Cv and Cp, you can get the internal energy, you can get the internal energy and enthalpy changes. Using the first law, which is Q minus W equals delta U, as well as the definition of enthalpy, which is U plus PV equals H, or H equals Q for a constant pressure process, and U equals Q, or delta U equals Q for a constant volume process, you can calculate relevant quantities or change in the state variables or the amount of heat and work transferred, which are path variables in this system. And we'll see this through examples later. Examples during lecture. Okay? A small closing note. Usually the ratio of Cp over Cv is used because it's a quantity that is going to appear in many formulas. We give it a symbol K. It's the ratio of specific heats. Ratio of specific heats. Okay? It's usually more relevant for gases. Okay? So, summary for module 4. I strongly recommend you looking at page 195, where there is a nice summary in the textbook. Okay, I would strongly recommend you taking a look at that. It has all the formulas that we saw in this unit. It has the relationship for work done. It has the relationship for the specific heats, Cp, Cv. It also has the specific heat for solids and liquids, which we just call C, and it also has the formulas for ideal gas as well as for substances with constant specific heats. So take a look at the summary. It's a very nice summary that will be useful for you to keep in mind what are these concepts about. Okay, and with that I would like to wrap up the lecture for this module. Please watch this video before you come to class. We will go through examples that illustrate these topics during lecture time. Thank you.